So good morning, Mubina, and tell me about Texas Instruments and current sensing. I mean, what is it and why is it important?
Yeah, so current sensing is a growing area. A lot of that is because of some of the trends that we see with and without electrification, but electrification is a big driver of that,
Yeah.
specifically for high voltage current sensing. So with high voltage current sensing, one of the big areas that hasn't really been as prominent as it is before is high voltage DC current sensing. AC side has existed for a very long time, but DC, there's not a lot of solutions that are available. So there are three main use cases that we see in current sensing. First one's protection, right? You want to make sure that you're not blowing up any circuitry downstream. You want to make sure your system's protected.
You said blowing up.
Yeah, because that is really what can happen sometimes if you're not careful.
Yeah. I want to make sure that, we all know that's coming if you're not careful.
Yeah, exactly. And when you want to do that, you want to make sure you're doing it fast, right? Because you want to be able to catch any sort of overcurrent situation as fast as possible. So speed is what people care about there. Another use case is for just telemetry, right? That's more so power monitoring, especially as we're hearing about trends like, making sure we're reducing our carbon emissions. We want to make sure that we're looking at power in every system and knowing what to go throttle in the case that you want to go and maintain it to be a lower level. And the last use case really is for control. Whether it's motor control, whether that's going from DC to AC or AC to DC, that requires you understanding what the current is in order to make your decisions.
Well, just to interject here, TI makes 90,000 SKUs, I think, some enormous, incomprehensible number. Is a portion of those just devoted to current sensing? Probably a big portion.
Some of it is, yeah. And that's kind of the beauty of it, is that no matter what current sensing technology that you're looking to use, TI has some play in that. So that gives you kind of the toolbox for you to go choose from as an engineer based on what you think is needed for your system.
Yeah, so what are the trends driving innovation in current sensing?
So one of them is electrification, so going from fossil fuel or mechanical sources of systems to more electrical, so that's one of them. Another one is kind of driven by that, which is renewable energy, specifically solar, which is very much DC as opposed to AC. So sometimes you may take solar energy, you may put that into a battery, and then you may directly feed that into whatever system, or you may convert that into AC and kind of use it as you do in your home from the wall. So there's many different topologies that you can do from that, but every single stage basically requires a current sensor to know kind of the validity of the measurement that you're getting. So that's one of them. Renewables and also automation, right? Really to make our cars be manufactured faster, to make really everything around us operate the way they do, we have to be automated. That means more motors, more robotics, all have current sensors for the control piece.
So even more basic than what you said, everybody has a sense of physics, I guess, in this audience, but you want a consistent current. That's one of the reasons for the sensor, correct?
Could be.
You want to modulate it, but also you know where it is being modulated.
Exactly, yeah. So part of it, and that's really the control aspect of it, is knowing exactly what it is every single point in time. For a control aspect, you may only want to know whenever it reaches a certain threshold. And so some of our parts also have an overcurrent comparator attached to it, so you only get a signal once it's gone over an unacceptable amount, or below an unacceptable amount.
Yeah, okay. Yeah, that's what my imagination told me it was. So when you mentioned your first use case example, that would be everything from converting a car from gas-powered to electric all the way to a big manufacturing facility changing over from gasoline or kerosene-based propulsion to electric, correct? Yeah.
Yeah.
And that is happening in industry, I think. What are some of the challenges for accurate sensing?
So it's very difficult to get accuracy and speed. So it's really the combination of the two, I'd say. Not just, you can have either or in a vacuum, but having both together, which is really what you want in order to get as close as possible to the true current, that is pretty difficult to go do. The main challenge when it comes to accuracy, specifically with Hall effect current sensors, is the drift, right? So you may have a good measurement in time zero, but as time goes on, as your temperature kind of goes on, you may see variances in your measurement, and that's very much not great, because what you have to do to get rid of that is calibrate. For temperature, you can calibrate, kind of characterizing it across your temperature spectrum, and you can do that way. That does require you to have external processing. But lifetime calibration is very difficult, because the only way you really do that is you just pause the system, and then you actually go and recalibrate in production, which is just a big pain.
Yeah, so you want to avoid those.
You want to avoid that. And so that's what we're really doing with our Hall Effect family.
Well, and you can step in quicker to avoid it, or if there's a problem, you can quickly react.
Exactly.
Yeah. So what are your products that address these high voltage power design challenges?
So this is our Hall Effect current sensing family, which is the TMCS 1123 family, which is the next generation of kind of what we already started with our TMCS 1100 family. So these are for higher currents. These are 75 amps at room temperature, high voltage as well, reinforced voltage.
Okay.
And the benefit is that we reduce that lifetime drift. So if you calibrate it at room temperature, you're able to get errors less than 1%, which has been unheard of in a Hall Effect space.
And acceptable.
Yeah.
Yeah, I mean, you want it down as low as possible. So what are the trade-offs between discrete and integrated? I guess you probably handle both, but...
Yeah. So we actually came out with this new family of products in our non-isolated space called Easy Shunt. And basically we use the lead frame itself to behave as the shunt, right? So normally how it works is you have to have a shunt resistor and then some sort of an AFE or a current sense amplifier to go then measure the voltage drop across the shunt and give you proportional voltage output. But what we're doing is we're using the lead frame of the device itself to behave as a shunt, and by doing that, we're able to be smaller, we're able to be more cost competitive. It's a simplified solution. So, of course, it sounds great, right? It's simplified. What's the trade-off? You're always going to get more flexibility whenever you have a discrete shunt. That's just the way physics kind of lays it out. I kind of think of it like taking a lens of a camera, right? You can autofocus, which is what an integrated solution is, and that gives you kind of a great answer. But if you want the most optimal answer, you have to have a lens that's perfectly defined for whatever you're trying to go look at, which is exactly what a discrete shunt is.
Well, that's really fascinating. Hey, thank you very much. Nice to meet you today.
Thank you.